All right, so you might say to yourself, like, why are we worried about constructing the real numbers? Like, we know that they're a thing. And the reality is, the construction of everything else is very straightforward. You can assume that, right, you can construct the natural numbers pretty easily. It's actually a little bit complicated and convoluted to do it, but you imagine you start with the number 1 and you add 1 to it, you get 2. You add 1 to it, you get 3. You add 1 to it, you get 4. And this is how you construct the naturals, right? And you're like, yes, I believe that I can do that. And then when you construct the integers, basically what you do is you just take the additive inverses of all those numbers, right? You say, oh, there's the number 2. So there should be a number -2, whatever that thing does. And so that's how you construct the integers, right? So now you have a whole number line of whole numbers. So that gives you the integers. From there, you can construct the rationals by basically taking multiplicative inverses. The way that we actually do this algebraically is we say that we take the field of fractions, right? So i.e. we take fractions. And so that's not crazy at all. We believe that we can do things like write a over b, where a and b are both integers and the denominator is not 0, right? Perfectly reasonable. But the reals are a completely different beast, because how do I go from the rationals to the real numbers, right? The real numbers, and what's our goal in constructing the real numbers? Well, we know that there are some numbers that are not rational, right? Pythagoras very famously had his whole big beef with the square root of 2, right? He like constructs a triangle, an isosceles triangle, where 2 sides have length 1, and then we know by Pythagorean theorem that the hypotenuse then is √2, and you can prove that that number is not rational. So obviously there are other numbers between the rationals, so we want to fill all those gaps. And in particular, one of the things that we want to do is we want to eventually get to something called the completeness axiom as well, which is, the super important axiom of the real numbers. And if you don't know what it is, don't worry, we'll talk about it. But basically, we need to fill those gaps. So how do you do that? Like, how do you just say, okay, I have the rational numbers, and here I'm at a very reasonable construction of these things, and then go from that to say, okay, well, how do I fill in those gaps? So this is actually quite complicated. It turns out this isn't straightforward at all. So the way that we're going to do it, there are a couple of ways that you can do it. And in fact, there are probably a couple of slightly more intuitive ways, but they require more machinery. DynaCanCuts we can access very quickly and with very little machinery, okay? So that's what we want to be able to do. And so let me just kind of set this up contextually by saying, where do we live? Okay, so we live in a world where the only thing that we know are rational numbers. So suppose we only know about Q. And we want to construct R. Okay, we want to actually build it. Oop. All right, so the way that we're going to do this is as following. So definition. Okay, so a real number and I'm going to do this weird thing where for real numbers, I'm going to underline them just, with this line to indicate that they're a real number, that I'm not thinking of them as a rational or an integer or whatever. We're obviously going to get rid of that eventually. I'm not going to underline all my numbers, all my real numbers, but for now, you'll see why this is important. A real number R is a subset of the rational numbers such that 1, okay, so it's closed downwards. So what that means is if y is a real number, or sorry, if y is a rational number in the real number R, and x is less than y, then x is also in the real number. And 2, no greatest element. Okay, so this means that if y is a real number, there exists some z with y less than z. Okay, so always, that's always true. You always can find something a little bit bigger. yeah, actually, is there an issue here? Oh, I need to say it's also proper and non-trivial. Let's just include those as a separate thing, proper and non-trivial. I'm like, why couldn't we have all of Q? It's like, oh yes, because it has to be proper, non-trivial. Our bar is not equal to the empty set, and it's not all of the rationals either. Okay. I'll often put proper and non-trivial first. So when we actually prove things, I'll probably prove proper and non-trivial first. Okay, and this is probably freaky, right? Because like, what the heck do you mean that a real number is a subset of the rationals? That doesn't make any sense whatsoever, right? That's really, really weird. So what these things are is they're called DynaCanCuts. And let me kind of draw one for you to try and give you an example of what this exactly looks like. So you can imagine if this is our number line, and it kind of, we're thinking of it as the real number line, even though we haven't constructed the real numbers yet. What I'm going to do is I'm going to find a point, maybe let's say 0. I'm going to choose square root 2, right? And again, we don't really know that square root 2 exists. I'm just doing this to help illustrate for you. So what I'm going to do is the real number square root 2 is the subset of the rational numbers of all the rational numbers less than the square root of 2. All right, maybe let me try and fill that in. So the number square root 2 is actually going to be the collection of all rational numbers such that x is less than 0 or x squared is less than 2. All right, and that's how we'd actually write this number down. And again, this is weird, right? This is probably really kind of freaky. But the idea is that once we construct the real numbers using this weird set theoretic definition and prove that they satisfy all the properties that we want them to satisfy, then we basically forget this weird set thing. And we go back to just doing, our manipulations of real numbers like normal, right? So we have to, unfortunately, use this weird thing in order to construct them and prove that they exist and prove that they do what we want them to do. But then after that, we'll forget about it. We'll never worry about it again. Okay, any questions so far? So hopefully you can see, right, that they're closed downwards. So what that means, similar to Taylor series, I mean, it depends on what you mean by that. I would say my first instinct is no, not similar to Taylor series, but if you can elaborate on that, then I'll happy to draw the analogy if appropriate. Are we using that there's a rational between every irrational and vice versa to give every real unique identity? Not yet. So we don't actually know this thing about rationals and irrationals yet. This is a density argument. We're going to prove this later. But right now, we don't even know that irrational numbers exist, right? Like we're constructing them. So we don't know about any properties of them because we just haven't built them yet. No, in this case, Salman, so with root 2, you mean? Root 2 is equal to this set, and it is a subset of Q. Right, so that's where the subset comes in. Right, but root 2 is going to be equal to this number. Yeah, I mean, that's tricky. Like, we don't know. And in fact, for most numbers, I'm not going to be able to formulate it in a nice way. But you imagine, again, if you kind of think about from having already defined the reals, like if you pretend you're in a world where you've now already defined the reals, I could certainly say take every rational number less than E, and that uniquely defines E. Like there's no other real number that will have the same subset of rational numbers, right? So for every real number, if I say take all the rational numbers up to that point, that's a unique set, right? There's one and only one set that does that for every real number because the rationals approach every real number, right? They can get arbitrarily close. So if you give me a different real number, I end up with a different set. And so in some sense, this is like an injective relationship, right? I'm taking, except I'm constructing them. But if you think about it again, in a world where the rationals or the reals already exist, you're going to map every real to the set of rational numbers that are less than it. And that is an injective mapping, right? That's the sort of idea here behind why we're using this construction. Like any real number contains lots of rational numbers, and Taylor series is a function of sum of lots of polys. Okay, yeah, okay. So there's a sense, sure, I think we could draw that analogy. in which we're like using the rationals to construct the real number by looking at all the rationals less than it. That's fair. But in some sense, most of the rationals less than root 2 are just coming along for the ride, right? Like -1/2 isn't really important to constructing root 2. It's just along for the ride so that it's closed downwards. But when you do Taylor series, those polynomials are actually critical, right? If you change the polynomial at all, you really change the function. So you could kind of think about it like that. I wouldn't say that that's an unfair way of thinking about it. But the rationals in the real number play, I would say, a different role than the polynomial plays in the Taylor series, right? Okay, so does that make sense? And this is why it's called the DynaCanCut. Okay, so basically the idea is you've got your list of rational numbers, and then you make a cut somewhere in your rationals, right? And that cut should define a real number. And this is how you're going to fill the holes, right? You're going to fill all the holes of the rational numbers by saying, for every rational number, I'm going to make a cut. And wherever that cut occurs, that is going to be a real number, right? And that's effectively what we're doing here. Now, you might say, okay, this is all well and nice, but like, how do I actually do anything with this? And it turns out, yeah, you're going to have to go and you're going to have to prove some things, right? So I'm not going to prove them all because there's way too many. But let me show you how such a proof would work. So theorem. If R, oops, underline, not overline, R and S are real numbers, then R plus S is going to be the set of all rational numbers such that X is equal to A plus B, where A is in R and B is in S, is a real number. Right? So what we're saying is, yeah, you can add real numbers. And again, you have to, when we say addition, what does that actually mean? Well, we're saying we're going to do this sort of set theoretic addition where we just take every possible sum that we can in R plus S. And that ends up being a real number, right? And this is going to define addition. And then once you have addition, you can prove all the things you want about addition. You can prove that addition is commutative. So you can prove that R plus S is S plus R. That proof's actually really easy. You can prove that addition is associative, so that R plus S plus T is R plus S plus T, right? So you can do all these proofs if you want. I'm not going to do them. I'm going to do this proof just to show you what a nightmare this is. And then I'll leave the rest as like exercises. Why not something like X less than 0 or X is less than A plus B? Well, you could. So that's going to define a set. Yeah, okay. So that's an interesting idea, and I think you could totally do that. But now you'd have to so that gives you a set, right? It seems to me like you're saying fix an A and a B, right? And then define R plus S as the set of all X less than 0 or X less than AB. That would be fine, but then you would have to union over all A's and B's. Because here, right, A plus B isn't fixed. A plus B is allowed to move. So A is allowed to vary over all the elements of R, and B is allowed to vary over all the elements of S, right? Yeah, so I mean, that would work, Mahmoud, but you'd have to take a union or something along those lines, but yeah. Okay. All right, so let's prove it. So proof. So we need to prove 3/4 things, right? We need to prove that it's a non-trivial proper subset of the rational numbers. We have to prove that it's closed downwards, and we have to prove that it does not have a greatest element. So like I said, I'm actually probably going to do proper non-trivial first. So one, let's do proper. No, let's do non-trivial. Right, so it's not the empty set. And so my claim here is this is clear. Since both R and S are non-empty, I never know how much I should say in these sorts of proofs, because some of you might be like, whoa, I don't understand that. And some of you might be like, yes, it's clear. So I'll default to being more clear. Since R and S are both non-empty, there exists some element in R and some element in B, or sorry, some element in S. So x equals a plus b is in R plus S, and R plus S therefore is not empty. All right, so I've shown that it's not the empty set. And again, we know that. Think about it, we're adding together these two real numbers. They're not empty, so when I add them together, their sum shouldn't be empty either. Okay, so now proper. Okay, again, proper means that it's not the whole thing, right? So how do I want to do this? So again, we want to use the properness of both R and S. So basically, we're going to say since R and S are proper, and S bar are proper, right? So let's say choose, I don't want to use A and B. What should I use? Let's maybe choose M. Choose M in Q that's not R, right? And then choose N in Q, not S. So basically what I'm saying here, I know both R and S are proper, so they're not all of the rationals. So in that case, I can choose an M and an N, which is not in, right? Not in R bar, and one that's not in S bar, right? We know that those have to exist. And now M plus N is also not in R plus S. Is not in, oops. R plus S. There's a bit of a logic jump there. You might have to think about it, but basically, if you really want the proof, I can do it. If M plus N is in R plus S, then basically what you can do is you can write M as M plus N. I guess I haven't really defined minuses yet, but basically you can jiggle it a bit in order to write R like M as a sum of things in R, and therefore, you can break it, and it's not going to be good. So if you want to, if you believe this, I as far as I'm concerned, it's fair to just kind of exclude it and to say like, yes, obviously this is true. But if you really, really, really want to be super rigorous, you can go through it and try and actually construct a contradiction. You say, assume that it is in R plus S, and then break something. But like, I don't think that that's worth doing. It doesn't matter. Okay. All right, let's do, which was the first of them? Close downwards, I think I wrote first, right? Okay, so let's do close downwards. Okay, so let's say fix a y in R plus S, and let x be less than y, right? So we want to show that x is also in R plus S. So that's what it means to be closed downwards. X here is implicitly irrational. So let's do this. So let's write y as a plus b, where a is in R bar and b is in S bar. Okay. So thus x is less than a plus b, or equivalently, we're going to have x minus a is less than b. Okay, and so you believe that. You might say like, well, okay, why do we care? Like, why have you done that? Well, look at this equation here. X minus a is less than b, and b was in the real number s. Since b is in the real number s and s is closed downwards, that tells us that x minus a is in s. Right, so thus x minus a is in s. And then x is equal to, let's see, so a plus x minus a, right? Why did we decide to fix y? Can we fix x as well? Okay, so like, let's look at, I'm going to just scroll up really, really quickly and I'll come right back. So in the definition for closed downwards, it says if y is some number, right? And I've kind of fixed it ahead of time. Then if x is less than y, x is in the real number, right? So the closed downward says, if you give me a fixed rational number in R bar, then every rational number less than it is also in R bar, right? So I kind of have fixed X here, but I've let them both be arbitrary, right? I've said fix some arbitrary Y in R bar plus S bar, and suppose that X is less than it. I need to show, for this to be a real number, I need to show that it's closed downward. So I need to show that X is now also in R bar plus S bar, right? That it is truly a DynaCanCut, that it includes all of the rational numbers that are less than it. Does that make sense? Okay, can you explain that one more? Yeah, so I'm basically, here, let me go back up to my picture. So the closed downward condition says, listen, if you give me any rational number here, so that's a fixed rational number Y, and then you give me any rational number X, which is less than it, X must also be in the set. No, I'm trying to show it's closed downwards, not closed upwards, right? So I'm going to fix, or you want to, maybe you're answering Ty's question of saying, like, if you fix the X, then you're kind of assuming that X is in the, right? Okay, yeah. Said X is a subset of Q. I don't think I ever said X is a subset of Q. Right? I don't think X being a subset of Q is ever said here. Do we not assume that is a proper subset in our second step? If so, is that not circular? So X here is a rational, right? X is rational. It's just a rational number. It's not a real number.
Sorry, I meant R. We said R is a subset of Q, right?
It is, yeah.
Right. So then in our second step, we're saying choose any M in Q, not R.
Okay.
So that's kind of assuming that it's a proper subset at that point, right?
Yeah, we know it is though, right? Because R and S are real numbers to begin with. What we're trying to prove is that R plus S is a proper subset.
Okay, all right. I was just wondering, because it seemed to me we sort of assumed what we were trying to prove almost in our step 2. Is that, okay. That could just be me, sorry.
No, it's okay. Like, this is a good point to clarify. So the theorem, we've assumed that R and S are real numbers to begin with, right? And then we're going to prove that R plus S has the properties of a real number. So we get all the properties of a real number with R plus S. We know that those are real numbers, and so we can access any of their facts. And, I'm leveraging that fact very heavily in order to prove all of these things, which is not surprising because that's the only definition of R plus S. Those are the only tools I have. So does that make sense, right? Like, we've for sure assumed that R plus S are real numbers. So we know they're closed downwards, proper non-trivial subsets with no greatest element, right? So we can use those facts for R and S separately. And then we need to combine them to show something about R plus S.
That makes sense. Thank you.
Okay, no problem. And Mahmoud, R bar is proper by definition? Right, exactly. Because we know it's a real number. We've assumed that it's a real number to begin with. Okay, are we all caught up? Are we good? Because let me put it this way. How else, maybe this will help. How else would you state closed downwards, right? Because in particular, by property number 2, that the set doesn't have a greatest element. So you can't just say, pick the biggest element of your set and every rational number less than it must also be in your set, right? We can't say that because by definition, we know that there isn't a biggest element. So how then do we say, look, it's closed downward. It has all of the rational numbers less than it. Well, what you say is, listen, give me a rational. And if you give me any second rational less than it, then that must also be in the set. Does that kind of make sense? I know that this seems like a convoluted way of saying it contains all of the rational numbers less than it, but, and if we had a greatest element, totally that would be easier, right? Because you just say, pick the greatest element and choose everything less than it, but we can't because we don't have a greatest element. Okay, and I'll actually give you all an analogy here in a second for that as well about intervals, because I suspect most of you don't actually know the proper definition of an interval because you've just never seen it before. But let me finish this proof and then I'll show you. So I've now written X as A plus X minus A. Remember, what are we trying to do? We're trying to show that it's in R plus S, right? So I'm trying to show that X can be written as something in R plus something in S, but yep, that's what I just did. A is in R, right? and x minus a is in S. So that tells me this thing is in R plus S, right? This is definitely the trickiest of the 4 proofs. Because I definitely have to use the closed downward property. Of course, I could have used it for R instead of for S, but I chose S. So this is interesting though, because it actually says you actually only need one of the sets to be closed downwards for this to work. Okay, well, so Yuanjie, you probably believe that x is equal to a plus x minus a, right? Like for sure, the a's will cancel and you'll just get x, right? So what I've done is this tricky thing where I've added and subtracted the a's. And so now here, listen, I'm gonna circle it in blue. So by assumption, we assumed that a was in R bar, right? We assumed at the very beginning that a was in R bar. And then over here, we also argued that x minus a was in S bar. And so now I've written x as being an element in R bar and an element in S bar, right? And that's what I need to do in order to prove that x was in R plus S, which is what I was trying to do. Does that make sense? Okay, cool. So our final one, the last thing we have to prove is no greatest element. And it's going to follow the usual thing. So we're going to say, look, both R bar and S bar have no greatest element. So, all right, so fix some y in R bar plus S bar and write y is equal to a plus b, a in R bar, b in S bar. Since R bar and S bar have no greatest element, I'm going to need letters. I guess C. There exists some C in R bar and D in S bar with A less than C and B less than D. That's a delta. B less than D. Okay. So again, stare at that for a second, convince yourself. I've said take Y and write it as an element in R bar plus S bar, right? And now forget about that for a second. Look at just R bar. Since R bar has no greatest element, there's something in it which is bigger than A, right? And that's what I'm saying here. There's something in R bar which is bigger than A. And same sort of story, S bar has no greatest element. So there's something in S bar which is bigger than B, right? And now hopefully you can see what's going to happen. A plus B is going to be less than C plus D. So thus, y is equal to A plus B is less than C plus D. And since C plus D is also in R plus S, then R plus S has no greatest element. Greatest element. And we're done. Right, and you can see like the pattern of every single one of these proofs. Every single one of these proofs is, I want to prove something about R bar plus S bar, and well, R bar and S bar satisfy those properties individually. So let's really exploit that and leverage that and use that to prove those same things about R bar plus S bar, right? Okay, everyone's fine? R bar, well, no, because they're closed downwards, right, Rui? So they have to go to negative infinity as well, right? Like R bar plus S bar can certainly be negative. It depends on what you mean. Like when you write zero infinity, are you talking about as a subset of the real numbers, or are you talking about as rationals? Right? Because they are themselves subsets of the real numbers. But yeah, what I'm explaining here is that, if R bar looks something like, so let's say R bar looks like this. This is R bar. And that if S bar looks like this, that like R plus S bar looks something like look something like that, right? This is what we're proving, right? That if I take two, basically you can think of it, if I take two intervals, one is like negative infinity to A, one is negative infinity to B, and when I add them, I still get something which is of the form negative infinity to something, right? That's the idea. Okay, everyone's all right? And this is a little bit tough. Yeah, this is definitely tricky. And if we were at St. George, I would make you prove all of these, but like we're not at St. George, and I don't think there's any value in that because we're not going to come back to these things. But again, I'm going to use this to prove the completeness axiom, and that's fine. Now, as an aside, which is not something I had planned on covering, but I think is useful. Yeah, that's okay. And I mean, like sometimes that's because it's hard to read other people's proofs. But if you can figure out where, Mary, just let me know and I'll go over it. But does anyone know what the definition of an interval is? Like, what is the definition of an interval of real numbers? Let's say, okay, let's go. We're going back to high school. Forget all of this. You all know what an interval is in some sort of heuristic way. But does anyone know the mathematical definition of an interval? An interval of real numbers. Anyone? You can all describe for me what an interval is, right? I think you all know what an interval is. But mathematically, how do we define it? Okay, Divyansh, this is a really good start. So a set which covers all possible elements between two numbers. So you're saying there exists an A and a B, and then the interval is all the points between A and B. Okay, so yeah, okay. So Yvonne and Alexander, yours both hold the open intervals, the finite open intervals, right? Okay, so are we saying that this is not an interval? Or is R an interval? And then what about this? Like, why did we exclude that set? That's an interval too, right? So, I mean, one thing you could do is you could say, okay, listen, I'm going to define the 4 types of open and closed intervals, right? So fully closed intervals, fully open intervals, and then the 2 half open intervals. So you could define that. That would take 4 definitions, but you could say these are all intervals. But then you have you have A to infinity, you have negative infinity to A, and then you have all of R as well. So if we want to do it this way, we could. These are intervals though, right? I hope you agree. These are all intervals. Right? So if you want, we could do it that way, but like we'd have to define 7 things and say these are the 7 types of intervals, right? And that sounds really, really crappy. What's the special property of an interval? Like what really is the defining thing that makes an interval an interval? Well, no, because R doesn't have any bounds. Okay, but then saying that A is less than or equal to X is less than or equal to B, that'd be the closed subset, but again, it kind of excludes R. Yeah, collection, a set, those are all true. Let me ask you, is this an interval? But R doesn't have any endpoints. So is this an interval? No, it's not. Why not? Okay, continuous, but what does like continuous mean here? It means there's no gaps. Is that fair? All right, there's no gaps in between. Because this isn't an interval. I hope we all agree. Right? It's a union of intervals, but it's not itself an interval, right? So there's an element arbitrarily close to every other element. Is this an interval? Right? Because the 2 numbers, right? Okay, so there's some yeses and there's some nos. I say this is not an interval. Even though the numbers are arbitrarily close to each other, this is not an interval because it has a hole in it, right? So the defining property of being an interval is that it doesn't have any holes. Do you agree? Like there's no holes in an interval. When you go from one end to another, no matter what you do, there's never a gap into there. And that's what some of you, I think, were saying about continuous, right? There's no jumps, there's no holes in the interval. That's why R is an interval, even though it doesn't have any endpoints, right? Like if you start at any point and you walk along, you'll never hit any holes. So that is the defining property of what it means to be an interval, okay? So the mathematical definition of an interval, and I'm going to show you, again, this is no problem if the interval, has endpoints, right? There is an infinite number of elements in an infinitely small range. I could still definitely break that though, right? Like I can break that with like 1, 2, union 3, 5. Here, this is basically true as well. Yes, 1, 2, union 2, 3 has a hole at 2. Yeah, exactly. Right? Because neither of those intervals include the number 2. So here's the definition of an interval, right? We probably won't use this, but definition, an interval. So you don't have to write this down. This is just purely kind of extra stuff. An interval, I, is a subset of R such that for every A and B in I, if Z is a real number such that A is less than Z is less than B, then Z is also in I. Okay, and again, you don't have to write that down if you don't want to. But, and you might say like, this seems like a really complicated way of writing down what an interval is, but no, it's actually easily the most elegant. So let's say this is your interval here, right? And maybe it goes off to infinity, you don't know. All you're saying is the important property of an interval is that it doesn't have any holes. So if you give me an A and you give me a B, then every number between A and B is in the interval. Right? That's what this definition says. If you give me any 2 points of the interval, every number between them is also in the interval. And you can see this is great because this doesn't care about whether the interval is infinite, right? It doesn't care about whether it goes off to infinity. It doesn't care about whether it contains its endpoints or not, right? It doesn't care if it is a closed interval or an open interval. It doesn't care about any of those things, but still captures the idea of being an interval, right? Because you can move A around, you can move B around. You're saying it doesn't matter. You give me any 2 points in the interval, everything between that is in the interval as well. Does that make sense? Do you see how this like defines an interval, right? You give me any 2 points in the interval, everything between them is also in the interval. So these don't have to be the endpoints, right? They don't have to be the endpoints at all. You're just saying any 2 points in the interval contains everything between them as well. And that, I claim, completely captures the idea of an interval. And if you remember, you might say like, well, okay, why are we talking about this? Is because when I was talking about there not being a greatest element, let's maybe even kind of switch this around so it looks like this. When we talked about there being no greatest element, how do I say that this, collection of rational numbers contains all the rational numbers less than it, especially given that it doesn't have a biggest element? Well, you say, listen, no matter what point, y you give me, if you give me some other x that's less than it, it's also in the set, right? And you can move y around, you don't care. So you can kind of move y as far to the right as you want to and effectively capture this idea that even though there isn't a greatest element, you've kind of like moved y all the way to the right fringe and said, look, everything less than y is also part of this set. Okay, so is this clear? Are there any questions about this? Like I said, we're not gonna like go and we won't use this fact too much in this course. I'm trying to think if anywhere. But right, this is mathematically how you get around these facts. If you can't nail something down like endpoints or a biggest element or whatever the case is, you say, okay, listen, I can't kind of pick the element. So why don't we just kind of ascribe our property, see if we can like write the property down in terms of arbitrary elements of the set, right? And that's how you do it. Okay. very worried because I'm not seeing a lot of like natural protest or questions but anyway, whatever, I'll assume it's okay. And again, don't hesitate to yell out and be like, yo, I don't understand. Okay, so there's a natural ordering. How would an endpoint be included in the definition? Well, I mean, like, it doesn't really have to be, in the sense that you don't care whether there are endpoints or not. But of course, if the endpoint is included in the definition, that's allowed to be A, right? And so you could still say, look, between any two numbers, A and B, every number between A and B is in the interval. If you have an endpoint, this is really, really nice because you could let A and B be your two endpoints, and now you're guaranteed that everything between them is also in there. But if you don't have your endpoints, then A and B basically just get as close to being the endpoints as possible, right? You just keep taking them further and further and further. And that captures the idea of the interval without having the endpoints and being able to use them, right? You don't. Because you've already assumed that A and B are in the interval, right? So you don't need to like use that definition to prove that A is in the interval. You know that A is already in it, right? Like it says right here, you've already kind of assumed that A and B are in the interval. Yeah, so you can just be like, you're still allowed to say, look, there are points in the interval. And if one of them happens to be the endpoint, great, but you don't have to somehow like prove that the endpoints are in the interval because you just know that they're in there to begin with. Yeah, I mean, there's lots of things where once you see the answer, it's obvious, but like coming up with the answer maybe isn't. If we had more time, I would have made you figure it out yourselves. But I think we did. Like as a class, we kind of came up with it collectively. I kind of jumped it and maybe wrote it out in its totality, but only because this isn't something we're super worried about. But yeah, hopefully it's clear. Hopefully it's not like too complicated. Okay, I need to define an order relation. So just very quickly, if R and S are real numbers, we say that R bar is less than or equal to S bar if R bar is a subset of S bar, right? Okay, my less than and subset look pretty similar. So let me maybe make that a little bit more clear. Okay, and again, I don't think that this is crazy. You probably believe that that's true because again, we're going to say, look, a real number, maybe that's a real number. Maybe that'll be our S bar. Maybe this will be our R bar. And yeah, I mean, if one is a subset of the other, then we know in our real number world that that real number R is less than the real number S, right? They're closed downwards. So if R is a subset of S, then R must be less than S, right? But in our case, we're actually going to define our order relation, the less than or equal to sign, by saying, look, this is true. And you could do strict inequality too if you want, right? So you could say R is strictly less than S if R is a strict subset of S, right? So you could do that as well. That's totally fine. And actually, this is the important point for no greatest element. If you don't have the no greatest element property, then you can have multiple sets be identified with the same real number, and then you're in trouble. Can we say if and only if here? Yes, but simply because anytime you're dealing with a definition, it's implicitly if and only if, right? Like it's a definition. So you're saying this is what it means to have this property. This is what it means to be less than. So it's automatically an if and only if. All definitions are. Yeah. So you can say it if you want. Okay. Now what I'm going to do here very quickly is I'm going to show you how to multiply. I'm not going to prove anything about multiplication, but in case you're wondering, like, how do I multiply? It's very similar in the sense that you want to multiply the sets, but it ends up being just a little bit different because you have to be careful about negative numbers. So believe it or not, the next thing we're going to define is the absolute value. So if R bar, let me cheat now and start using R for the real numbers. Then we define the absolute value. Oh no, I have to define the negative first, right? then we define negative r. This one's going to hurt. This one's going to hurt your brains. X and Q. Let me just make sure that I don't do the wrong thing. X and Q is such that negative X is not in R bar and X is not the greatest element. Or is not the least element. Is not the least element. Of Q not R. Okay, so that's the definition of the negative. And you're going to have to parse that for a second and be like, whoa, what? But again, this definition actually very much does make sense if I think you just got to draw a number line. Right? So again, here's our number line. We really have to indicate 0 here. So here is my R bar, right? And it is all the rational numbers less than that. So this is closed downwards, but only to 0. No, it actually is going to include everything less than that as well, right? So if that's R bar, we want this to be negative R bar, right? So we know that that's true. So this set here, this is Q not R bar. So we're going to say, look, this point X is in negative R bar if, well, where is negative X? Negative X is over here. So we want negative X to not be in R bar, right? If you take any point in negative R bar, maybe let me draw it like this. So if negative R bar is this set, then when you look at the negative of that set, I know there's way too many negatives going on, you get this, right? This is the negative of negative R bar. Right? Does that make sense? Does everyone see that? That the negative of negative R bar is Q not R bar? So what we want to say is that X is in R bar if negative X is not in R bar. Right? So X over here is in R bar if negative X is outside of R bar. And because Q not R bar actually does have a least element, that least element will map to this greatest element. And we need to make sure that we don't include that because we're not allowed to have a greatest element, right? So we also say, oh, you're not allowed to be this endpoint. Does that make sense? This one's a little bit tricky to think about because obviously when you you need to take negatives, which is going to reflect things about 0, but you still need it to be closed downwards. So it's almost easier to start with the definition of what you want negative R bar to be and see if you negated that, what would that look like in relation to R bar? Okay. And the negation is the complement. It's the collection of all things which are actually bigger than R. So that the least element is in R. Okay. So I'm not quite certain what you're asking, but let's say this. So there is a least element, right? Because R does not have a greatest element. That means its complement does have a least element, right? Or could have a least element. Now that least element, remember, we want all of this green stuff to become the white stuff on the left. Okay, so this green stuff, when we negate it, is going to become the white stuff on the left. And I do not want this point to become this point because that would then be a greatest element. And then negative R bar would have a greatest element and wouldn't be a real number anymore. So we're just saying, listen, ignore this endpoint here completely. You're just not allowed to take that so that we don't have a greatest element when we take the negation. Okay, so now I can define the absolute value. So definition, if R is a real number, then the absolute value of R is R if R is greater than 0. And yeah, oh yes, the R does, right, exactly, okay. And negative R if R, well, let's say greater than or equal to 0. if R is less than 0. Okay. And 0 here is, like, I didn't say this explicitly, but clearly every rational number can be identified with the DynaCanCut at that rational number, right? So the real number 0 are the collection of rational numbers less than 0, right? And the real number, or the real number 1/2 are the rational numbers that are less than 1/2, right? And the real number 7 are the rational numbers less than 7. So when I say 0 here, that's what it is, right? This is the real number 0, which is the rationals which are less than 0. So this is the absolute value, and then you say the following. So this is a lot just to tell you how to multiply real numbers. So definition. So if R bar and S bar are both greater than or equal to 0, there's a lot of under bars, right? Then R bar times S bar is what you think it should be. So it's going to be the set of rational numbers such that X is equal to AB, where A is in R bar and B is in S bar. Okay. And again, for this to work out and to be a rational number, both R and S have to be greater than or equal to 0, right? And you can check, try to make sense of this, just like, think about what this would be if one of them was actually negative, and you're going to see you're going to break closed downwards, right? It's going to immediately just screw everything up because one of your numbers is negative. So it's actually going to flip the closed downwards to being closed upwards, right? So you need them both to be non-negative, but then you say, okay, but like clearly we can multiply two negative numbers or a positive and a negative number, in which case you say the following, and in general, R bar times S bar is equal to the absolute value of R bar times the absolute value of S bar if R bar and S bar are both less than 0 or are both greater than 0. Right, so they have the same sign, and then negative R bar times S bar if either R bar is greater than 0 and S bar is less than 0, or R bar is less than 0 and S bar is greater than 0. And then you define it to be 0 if either R bar is 0 or S bar is 0. Right? What a mess. But basically, you're just making sure it's always, that the numbers that you're multiplying are always positive. Now, certainly, you can see in this middle case here, if one of the numbers is negative, your answer had better be negative as well. So what you're going to do is you're going to multiply the two positive numbers and say, oh, I need to fix it because I know the answer should be negative. So then I'll take the negative of it, and voila, you're done. Okay. So this is, you can see, you don't ever want to prove anything about multiplication because what a mess, right? This obviously is going to take a lot of work in order to sort anything out here. So, okay, this is, I think, a good breaking point because I'm sure all of your brains are just frizzled into ash, and you have to like hold your ears, otherwise the ash is going to blow away, sort of thing. And that's okay. Like I think I've fried your brains. Why is there RS greater than or equal to 0? Just to like include every possible case, right? Like you're right, when R and S are both greater than or equal to 0, we already know how to multiply. So what I'm saying is this is like the general definition that covers all cases, this bottom one. But in order to even define it, we need to know how to multiply non-negative real numbers. And so, well, okay, you're right. I'll take out the equals. There you go. Yeah, you're right. I shouldn't, if I have the equals case separately, I shouldn't include it. You're right. Okay, so what we'll do, yeah, perfect. Let's take 10 minutes. When we come back, I'm going to do the completeness. Basically, I'm going to talk about order relations on R. Like we're going to ignore this for like a second. And then I'm going to proof for you the completeness axiom. So the completeness axiom is one of the most important things that we have. It's called an axiom, but it's not, it's a theorem. And so we'll prove that. That will be the last proof that I do using this crazy real numbers as sets thing. And then we will leave that behind and never worry about this stuff again, right? But we just need to know the completeness axiom is true. And then I'll talk about soups and imps and all that sort of stuff. Okay, so 10 minutes. By my watch is about 10:08 now. So 10:18 will come back, but otherwise just set your watch for 10 minutes and we'll come back. Okay, so I'll see you all in 10. Yes, 10 minutes to find yourselves again. Okay, so we're gonna start again here. I think maybe though we should do something slightly different just for a bit to give our brains another chance to recover and maybe give you a chance to prove something and build your confidence back up. So that's fine. In terms of talking about real numbers as sets, everything is weird, everything is crazy. Your world has been like, turned inside out and nothing makes sense anymore, and that's fine. Now, we defined this order relation by saying R was less than or equal to S if the subset R was, if the set R was a subset of the set S. Does the multiplication of positive R and S involve only positive A, B, and R and S? No, it could be anything. Oh, wait, actually, you know what? You might be right, because then otherwise, right, if you have arbitrary large negative numbers, then they would give you arbitrary large positive numbers, which would give you an issue, right? Let me just double check my notes here. Right. If R and S are greater than 0, set of rational numbers such that X is less than 0, or X equals A, B for A and R and B and S bar. Let me check. You're right, though, that could be an issue. So you might be right that we only take the positive parts of them. Book. X is equal to AB for A and R. Yes, AB both have to be positive. You're right. Good call. Very good call. So here we're going to take AB to be greater than 0. Very good call. You're right. I mean, we're not, no. So to prove that it's a field, we'd have to prove that addition is associative, multiplication is commutative, multiplication is also associative. We'd have to prove that multiplication distributes over addition. And so all of these, you remember how long this proof was, right? And there are like 10 more of these, and they're all worse than this one. Not all of them, but some of them are worse than this one. So this would be like something we'd spend the next couple of weeks doing. So I'm not going to worry about it, but I would say like choose your favorite one and do it, right? So if you want to prove addition is commutative, that's a great one. If you prove that addition is commutative, that one's actually fairly trivial. Prove that addition is associative, that's a good one. That's a fun one to try. Multiplication is like just defined. You can prove that these are real numbers, right? I didn't even prove for you that the product of two real numbers is a real number. So you might want to try that. But yeah, we're not going to prove them all because, it takes a long time. But what we're going to do here is like, let's tangential sidestep. We have another definition of what it means to be, why aren't we proving R minus S and R divided by S? Is because we can also, yes, right? Like R minus S is R plus negative S. And we're not going to prove anything about multiplication because multiplication is hard. And yeah, sure. Like you can prove the existence of inverses. I mean, basically, yeah, I'm going to leave you to prove that. How do we know what needs to be proved and what is trivial? It all needs to be proved. And you won't know what's trivial until you actually start proving it, right? But Jay, like what you can do is basically you can prove that 1 over S exists and then that S times 1 over S is the multiplicative inverse. You could do it that way if you really, really wanted to. This is what I'm saying. There are way too many axioms. We don't want to prove them. And anything involving multiplication is really, really hard, okay? I think Spivak has most of them. Like if you really want to dive into it, go see if you can find, a copy of Spivak. and it's at the back of the book, right? It's in like the appendix. And I think he has most of the proofs, but they are like not easy. And SpivX sometimes overcomplicates things, but whatever. Like, in fact, my proof of the completeness axiom is very similar to SpivX, but SpivX just, again, makes this unnecessarily complicated, and I don't know why. But okay, we're not there yet. So what we're going to do is let's zoom out, and I want to do this just to give your brains a little bit of recovery. Let's stop thinking about real numbers as sets for now. Let's just think of them as numbers the way that we did an hour and a half ago when life was so much easier, right? And so we're going to define an order relation on the real numbers. So definition, let P be the set of real numbers such that X is greater than 0, right? And we say that X is less than Y if Y minus X is in P. Okay, so this is an example for those of you who are asking about that like first bonus question on the assignment. Not bonus question, but like extra exercise problem. This is an example of a positive set. Okay, so you can you can have the following properties. So note. So we know the following facts about P. And I'm not going to prove these, you can. Following facts about P. 1, if X and Y are elements of P, then X plus Y is in P, and X times Y is in P. And 2, if X is a non-zero real number, then either X is in P or negative X is in P. Okay, so this is an example of a positive set, and the definition of a positive set is precisely these two properties. Okay, so the sum of two positive things is positive, the product of two positive things is positive, and then every non-zero thing is either positive or negative, right? It's negative is positive. That's the definition of a positive set. Now, in that, I don't necessarily want to go through the definition of what a field is, but you can define a positive set for an arbitrary field in precisely this way, and then use it to define the order relation above, which is X is less than Y if there are differences in your positive set. Okay, so let me just kind of make the following comment. This agrees with our order relation defined above. So this agrees with the relation R bar less than or equal to S bar, or let's just say less than S bar, if R bar is a strict subset of S bar. Okay, so the relation that we had above, where we said that two real numbers are related to each other in this way, if one is a subset of the other, agrees with this one. Okay, and you can prove that if you want. Let's not worry about it. Hopefully you just are like, yes, they both definitely make sense. So using the definition read here at the top of the screen, sorry, what is relation? Like in our case, I'm saying like R is less than S. So the relationship between them is one is less than the other. But if you go back and if you look at like the formative thing that I sent out way back when, before class even started, it's that same notion of a relation. But yeah, otherwise you can just say less than. R is less than. This agrees with the less than sign that we defined from defining the real numbers as sets. Okay, so you can take it to mean that. So don't use the blue, don't use the set definition, and prove these theorems, or prove this result. So suppose, how many numbers do I need here? Do I need 4? X, Y, okay, so suppose X, Y, U, V are in R, and C is greater than 0. then 1. If, and we're going to prove transitivity, if x is less than y and y is less than u, then x is less than u. 2. If, what I want here, right. If x is less than y, then cx is less than cy, and 3. If x is less than y and u is less than v, then x plus u is less than y plus v. Okay? Yeah. Oh, you know what? Maybe, let me write this out, relation. I didn't even realize I'd abbreviated that. Okay, so don't do this using the crazy definition that we just did. Okay, I want you to spend 5 minutes and see if you can prove this. Prove this using that red definition right there. Okay, and again, you can use the properties in white. And I'm going to give you 5 minutes and I want you to practice that just to see what sort of progress you can make. And hopefully this will build some confidence and you'll be like, oh, okay, I can prove these. I hope, we'll see. Okay, so 5 minutes. And again, don't hesitate to throw any questions in the chat if you're not certain about what to do. Okay, so hopefully you can see here why we use this notion of positive sets, because even what I've written just to try and make your lives a little bit easier is automatically circular, right? If you look at the definition of P, I've said it's the set of all real numbers such that X is greater than 0. And then I'm going to use the set P to define what it means for X to be less than Y. This is circular though, because the definite, right, in order to define the less than sign, I had to use the greater than sign in the definition of P, right? So this is a circular definition. But what you would just say instead is, look, P is some positive set, and we know that a positive set exists, and we can prove that a positive set exists. We can't like use the greater than sign to define it, but we know it should be all the numbers to the right of 0. And then this is why we use this thing of saying like X is less than Y if Y minus X is in P, because we don't have a notion of less than or greater than until we actually define it. That's why we use this stuff about positive sets. And you might say like, why do we do that? This is the reason why. Okay. So hopefully you gave this a shot. Again, I'm going to go through this just, you've probably never in your life had to worry about these sorts of proofs because you're just like, yeah, they're obviously true, or you were told they were true at some point. Well, let's give it a shot. So in 1, we know right here are our hypotheses. So we know that X is less than Y. So we know if we translate that, that means that Y minus X is in P. And we know that Y is less than U. So U minus Y is in P. And then we want to show that X is less than U, i.e. we want to say something about U minus X. Right? I want to show this is in P. And I say, okay, well, the two things that I know about both have Y's in them. So I'm going to add and subtract a Y. Right? And now both of these things are what I know about. They're both in P. And by the properties of P, we know that the sum of two things in P is still in P. So that's what we wanted to show, right? 2, so if X is less than Y, then CX is less than CY. Again, so we know that Y minus X is an element of the positive set. We want to say something about CY minus CX. Right? We want to show that that is in the positive set. The obvious thing to do, I think, is to factor out that C. And now we know that C is in P, right? We're actually told that it's greater than 0 to begin with. And then we know that Y minus X is in P because that's what we were told. And then we were told, oh, the product of two things in P stays in P as well. So that's in P. And then finally, so we know this one, I think, actually, it looks like it might be the most complicated, but I don't think it is. So we know that Y minus X is in P, and we know that V minus U is in P. Now we want to say something about this x plus u being less than y plus v. So we want to show that y plus v minus x plus u. We want to show that this is in P. And of course, we're just going to be clever about how we bracket things. V minus, oops, that should be V. V minus u. Both of these are in P. And the sum of things in P stays in P. So we're done. Right? So now we've proven some of these relation inequalities on the real numbers, which is nice because again, you probably knew these things were true, but if you actually have to prove them, this is how you go about it. And again, you can do this in an arbitrary field. So if you have a field anywhere where you can define a positive set, then you're good to go. And you can just, all of these things now you know are true. Any questions? Because otherwise I'm going to prove the completeness axiom. This was supposed to be just a brief reprieve from the construction of the real stuff, but we're about to do that again because I need to prove the completeness axiom. Anti-trauma measures. Yes, there was a very real sense in that in which that's exactly what they were, right? I'm trying to, you know, if you didn't get them, that's fine. Like, again, you probably haven't played with these before, but they're just to build up your confidence again before I crush it. So like, you know, you were bleeding and now we stuck a Band-Aid on it and now I'm going to rip the Band-Aid off and, you know, make the wound worse. Okay, so the completeness axiom. And again, it is called an axiom. It is really a theorem. So theorem, oh, I guess I have to do a definition first. So definition. Now for this definition, you can use either of the definitions that we just did in terms of either the reals being subsets of the rationals, and then R is a subset of S is the same thing as R being less than or equal to S, or this definition that we just did. You can use either of these and it's fine, okay? So if, this is important, so use the definition that you're most comfortable with. So obviously, probably the one we just did. If S is a subset of R, we say that M is an upper bound for S if for every S in S, S is less than or equal to M. Right? Okay, that's nice. Right? That makes sense. Right? You're an upper bound for a set S if you're bigger than everything in S. Right? That's not crazy. If S has an upper bound, so in that case, we were defining upper bound. So if S has an upper bound, we say it's bounded from above. Bounded from above. Okay, so that's the definition of being bounded from above. All right, if S is bounded, from above, its supremum is its least upper bound. All right, so what I mean by that, well, I should say denoted sup S, like that. Yeah, this is, yeah. Does M need to be an S? There's nothing saying that M needs to be an S. Nope. An upper bound can be any number. It does not need to be in the set itself. It could be like way beyond the set. So you imagine if you have the interval 0 to 1, 7 is an upper bound for that set, right? Even though it's definitely not in the interval 0, 1, it is still an upper bound. And then Mary, the sup is the least of the upper bounds, right? Yeah, you can feel we're getting close to the limits, right? You can feel it coming. So its supremum is the least upper bound, denoted by sup S. And I'm going to say that is if M is any upper bound So what I'm doing here is I'm actually defining what it means to be the least upper bound. So if M is any other upper bound, then the sup of S is less than or equal to M. Right? So this was what it means to be the least upper bound. So the supremum of S is an upper bound, and amongst all upper bounds, it is the minimal one, right? It is the least of all the upper bounds. So it's kind of weird because you're like simultaneously bigger than everything in S, but you're smaller than all the upper bounds. So you kind of see, there's like a sandwiching going on, right? You're bigger than everything in S, but you're smaller than all the upper bounds. And of course, we can draw something like this. You can imagine here's our number line, right? And maybe our set S looks something like this. And maybe it's got like a couple of weird extra points here. Okay, so maybe this is S. You know, this point here is an upper bound, right? This is an upper bound. But it's going to be this point. This is the supremum, right? This is the least upper bound. It is the least ranking supreme overlord. Sure. I mean, I tend to think it's actually in some sense the best overlord, right? It is the one that most efficiently reigns over the set S, right? It doesn't, like M over here in this drawing is just way too overbearing, right? It uses too much strength, whereas the supremum uses exactly enough, of a ruling hand. So in my mentality, the supremum is truly the best of the upper bounds. Okay, so does that make sense? So you can see, in fact, everything over here is an upper bound, and the supremum is the smallest of them, right? It is the one that is the most to the left. Now, without saying everything, there's an obvious analogy of everything in the above definition, but for bounded below. And I'm going to put obvious in brackets, but I think it is obvious. There's an obvious analogy for lower bounds and being bounded from below. And if you're really not certain about it, exactly, and it gives you the infimum. And I would say, if you're not certain about what it is, take an opportunity to try and write it out. And then you can ask me, hey, did I get this right? And I'll be happy to go through it and check whether you're right. But there's an obvious analogy for lower bounds and being bounded below. In which case the greatest lower bound, is the infimum. Okay, and in this picture, right, the infimum is right here. Yes, okay, I share the most privileged peasant. So this is, and again, I'm not going to rewrite out that whole definition, but with lower bounds and everything, just switch the inequalities as appropriate, change above to below and supremum to infimum, right? And greatest to least, and et cetera. And again, if you're not confident in what that, analogy definition should be, write it out, send it to me, bring it up to me whenever, Piazza, office hours, and I will be happy to check it for you. And now the completeness axiom. Okay, every non-empty, and the non-empty part is important. Every non-empty set which is bounded from above has a supremum. Okay, so the completeness axiom says every set that could have a supremum does have a supremum, right? If there is an upper bound, then there is a least upper bound. And again, this should somehow feel like, yes, obviously this is true, but we have to prove it, right? This is not, turns out this is not in any way obvious, and it comes directly from the way that we constructed the real numbers. Okay, so does everyone understand the statement of the completeness axiom? And of course, from the completeness axiom, again, the direct analogy holds. If you're non-empty and bounded from below, then you have an infimum. Okay. For those of you who want to try and prove that, you absolutely should. Do not imitate the proof I'm about to give you. There is a very easy proof of the analogy version for infimum from this theorem. So once you get this theorem, use it to prove the infimum version. Don't prove the infimum version from scratch. Okay. All right. Out of curiosity, so now we have to go back to the construction of the real numbers. Everything is going to be a subset of the rationals. What do you think should be the supremum? Can anyone, like, we have to construct it, right? We're going to prove it exists, but in order to do that, we're actually going to construct it. Can anyone think maybe what would a good candidate be for the supremum? It's a tough one. I think when I write it out, you'll be like, oh yeah, that probably will work, but maybe you have to see it first. R bar, okay, but R bar is a single real number. And now, so like here, let me give the setup. So let's say let S be a subset of the real numbers, which is bounded from above. Non-empty. Okay, and maybe part of the thing that's going to scare us here, X such that X isn't in R, but for, okay, but so Yvonne and Stephen, these are both single real numbers. Now we have sets of real numbers, right? So we have sets of sets. Every real number in S is itself a set. And so S is a set of sets, right? Okay, here's what we're going to do. Define, I'm going to call it sigma. It's going to be the union over all the alphas in S of alpha. So I'm going to, well, but what if some of them are naturals, right? So we kind of want them to get closer. So basically what I'm saying is we've got, you know, if you kind of go up to this picture here, right? Each of these blue numbers is itself, you know, a set of things like this, right? And so what I'm saying is to get the supremum, what I'm going to do is I'm going to union all of those cuts together, and the union of them should be this cut right here, right? And that cut is the supremum. That number, whatever it is, once I've union all of those cuts, that is going to be the one that is in some sense the biggest cut. Does that kind of make sense as to like why that would be our candidate? That's the one that we want to try and work with. Okay. Yeah. And so this is actually going to make our life super interesting. And I think this was the part too that Spivak makes totally unnecessarily complicated. Like he doesn't define it in terms of the union, but it's totally the union. So, all right, let's prove what we want to prove. So number one, this is non-empty. That's trivial. Since S is non-empty, there is some non-empty alpha in S, and alpha is a subset of sigma, so sigma is not empty, right? The set that we're working with is non-empty, so it has at least one real number in it. Every real number is non-empty because it's not allowed to be, and so because that real number is part of the union, S is not empty itself. Two, it's proper. How do I want to do proper again? Right. So since S is bounded from above, I'm going to call it mu. We're kind of like doing Greek letters for my things right now. So let mu be an upper bound. Right. So that is that alpha is less than or equal to mu for all alpha and S. Okay, so in particular, that must mean, is that how I want to do this? Let me just check my notes here. Alpha is less than mu for all alpha in S. Since mu is in R, there exists, right, okay. So since mu is a real number, there exists some X, some rational, such that X is not in mu. Right? Because mu is itself proper. Now, every alpha being a subset of mu then says that X can't be in any of the alphas. Right? Because if X was in any of the alphas, then it would be in mu. For all alpha. And so X is not in sigma because it's not in any of the alphas. X is not in mu? Okay, sure. So X is not in mu. Mu is a real number. And one of the properties of real numbers is that they are not all of the rationals, right? They are a proper subset. And because they're a proper subset, there must be some rational number that is not in mu. Does that make sense? Okay. So how far do I have to go here? It's probably at the very beginning. Right. This thing right here, right? Real numbers are not all of the rationals. That's one of their properties, right? There's no real number which as a subset contains every rational. Do you agree? Right? That's one of the properties. Right. And so there must be some rational that's not in there. Yeah. And so because mu was a rational number, it was one of the rational numbers, then there must be some rational number that's not included as part of it. So this one's a little bit tricky, but you're basically like, look, there's this X that isn't in mu. And since it's an upper bound, since mu is an upper bound, all the alphas are subsets of mu's. So if X is not in mu, it can't be in any of the alphas. And that's basically just the argument, right? As a picture, you've got like, here's all the alphas, right? Here's sigma. It includes all of the alphas. Mu is right here, and then X is right here, right? And so, yeah, certainly X is not in sigma because it's not in mu, and mu contains all the alphas. So that's the argument. That's kind of the picture there. Okay, 3. So closed downward is usually the next one. So closed downwards. These ones, surprisingly, I think proper is actually the hardest. So closed downwards, I think, is the easiest. So closed downwards. So fix some y in sigma and let X be a rational number with X less than Y, right? We want to show X is in sigma, right? That's the property that we want to do. That's what it means to be closed downwards. Since Y is in sigma, there is some alpha in S such that Y is in alpha, right? Because sigma is the union over all the alphas. So if Y is in sigma, then in particular, it has to be in one of the alphas. Since alpha is closed downwards, and y is in alpha, so x is in alpha as well, and hence in sigma. Right, that's what we wanted to show. And then for no greatest element, and the no greatest element and close downwards are almost exactly the same proof. Right, so we're going to say let fix y in sigma, and we're going to show that there's something else in sigma which is bigger than it. There exists some alpha in S with y in alpha. Since alpha has no greatest element, there exists some z in alpha with y less than z. But z in alpha implies that z is in sigma, right? Because sigma is the union over all the alphas. And so we're done, right? Because now we've shown that z is an element in sigma, which is bigger than y, so it has no greatest element. All right, so this tells us, this does not prove it, our result. This proves that sigma is a real number. Right? We still need to show that it is the least upper bound. We have to show that it is the suprema. We need to show it's the least upper bound. Okay. So first of all, it is an upper bound. So note that alpha is a subset of sigma, implies alpha is less than or equal to sigma for all alpha in S. So sigma is an upper bound. Right? Now we just need to show it is the least upper bound. So suppose mu is some other upper bound. Okay, so in particular, that means that alpha is less than or equal to mu, or equivalently, alpha is a subset of mu for all alpha in S. But if every alpha is in mu, then so too is their union. And that, because sigma is a subset of mu, means that sigma is less than or equal to mu. Right? So it is an upper bound, and we've shown that for all upper bounds, it's less than or equal to any other upper bound that you give me, so it's the least upper bound. Thus sigma is the least upper bound. Don't know what that word is. Upper bound. And we're done. Okay. And there we go. Look at that. I'm about 30 seconds over, but there we have it. So we've proved now the completeness axiom, and I promise you that is the last time that we will construct real numbers and prove things about real numbers this way. I realize that might have fried your brain a little bit, but you needed to see the completeness axiom and know that the completeness axiom was a thing. We will use the completeness axiom a lot. On Thursday, we're going to talk about suprema and infima a little bit more, not in this way, but like, how do we actually use them? How can we practically implement suprema and infima in order to be able to compute things and do things? And as was kind of commented, you can start to see limits encroaching here. Okay, so that's the idea. And if you want to do a little bit of reading ahead, by all means, go look up sups and ifs. They can be something that I know that students struggle with a little bit. So doing some reading ahead of time isn't too bad. If there are question on test business material, what would it be like? I mean, you could imagine I could actually ask you to prove a property of the real numbers. Probably not a terribly hard one, but I could certainly do something along those lines. No problem. All right, everyone. So thanks for coming out. Yeah, like I said, I'll see you all on Thursday. Don't hesitate if you have any questions. Like I've already had my 157 office hours for the week, but I am answering Piazza still. So if you are still struggling with questions, especially I know a lot of you were having issues with question 2 of the assignment, don't hesitate to throw some stuff on Piazza and I'll happily answer you. Okay. And yeah, thanks everyone. And I'll see you all on Thursday.